Okay, good morning everyone. Today we're going to be looking at the series parallel circuit. All right, now for us to be able to work out what we need to work out in this session, you guys will need to have covered the series individually on its own lesson together with the parallel on its own, because the skills you will learn in both of those sessions are really important to be able to complete what we're going to complete today. The series parallel is more complicated, but it's less often seen. So as long as you get good at the series on its own and parallel on its own, that's the most important, right? This is just a bit of a test to make sure we can use those skills. All right, so you guys should be able to see my shared screen. All right, it's our PowerPoint as usual. Today we're going to be looking at the series parallel circuit. And what we're going to do, we're going to look at the circuits themselves to see what it actually means for it to be a series parallel circuit. We're going to calculate voltage, current, resistance in series parallel circuit containing just the resistors. We're going to change the circuit from what looks like a complicated circuit with maybe 3, 4, 5, or 6 resistors, for example. We're going to simplify that to a circuit, like we've said before, with a single equivalent resistance. All right. And then once we've done second point, we've got the voltage, the current, and resistance. And with the voltage and current values that we've worked out, we were able then to calculate the total power and the power taken by each component in the circuit. All right. We'll also be looking at the faults in the circuit. We should already be pretty good at this because if we understand series circuits and we understand parallel circuits, then we'll understand what happens to a series parallel combination if there's a fault there. All right, and then we're going to finally look at the uses in the industry. Okay, so move on. So we have an example of a series parallel circuit here. The reason it's a series parallel circuit is because you can't say that it is just one of the two. All right, so starting at the position, you've got your voltage source, which is connected to 2 lamps that are in parallel, lamp 1 and lamp 2. And then you've got 3 lamps in this third leg, which are in series. All right, so we need to work out the current. Remember, in an equivalent circuit, in a circuit with a single resistor, we need to be able to work out the current. Okay, so at the moment, I can't just work out the parallel part because I'm stuck with this. All right, I can't work out this bit because I'm stuck with that. All right, so we need to combine it all into a single resistor. And then we'll be able to work out the current, and then we can go from there then. Right. Excuse me, a series parallel circuit with 3 branches, 1 branch having 3 lamps in series, as you can see. All right. The laws for series and the laws for parallel apply to the part of the circuit which matches. All right. Okay. So series parallel circuit, you don't necessarily need to write this stuff down. All right. It's the working out which is important today. Can involve any arrangement of series or parallel connected components, and often needs to be simplified. It has to be simplified. So voltage, current, and resistance values can be found. All right, and that brings us on to this example here. Okay, so what we've got here, we've got a resistor there, which is in series then to this parallel leg. This parallel leg has R2, which is 400. It then has 2 resistors which are in series, which is R3 and R4. And then coming out again, we've got a single R5 then, which once again, it would be in series with these other parts. All right. So how do we do that? Okay, well, the first step, and I'm going to do this and annotate this for you. Okay. So the first thing we need to do, we need to work out how it's best for us to simplify this circuit. All right. So if you remember, and I'll write the rules up on the left-hand side for series. Resistance total equals, we add them up, okay, and so on. And then for parallel, it's 1 divided by RT equals 1 divided by R1 plus 1 over R2. And so on. All right, so we need to remember those two. Okay, So we're going to use these to simplify this into, remember, we always want to try and get it so the circuit looks like, I'll draw the battery in. They haven't drawn the battery in the picture, so I'll draw it in here. Okay. That's where our battery would be. So we've got our colors coming off. All right, so remember that we want to be able to turn the circuit here into a simple circuit. The simple circuit that we've talked about many times previously. Okay, there's my resistor there. I know it's not the best drawing. Come back to the line, and we'll have our positive. Come back to there. So remember, any circuit that looks like whatever the one on the right hand side looks like can always be simplified to look like this one on this side here. All right, and this is going to be the RT of the circuit. So this is what we want to work out first. Remember, we've got our steps. Okay, so step one, to make it easy for us, is to find RT. All right, there's a problem though. All right, to find RT with this circuit, you can't just add them up. You can't do your 1 over because it's a series parallel. There's a combination of both. All right, so the first thing we want to do is look at the circuit itself and try and identify somewhere which is simple for us to simplify. All right, now to me, there's not much I can do with this one. So I look in the parallel circuit. There's not much I can do with R5, so I look in this parallel circuit. Now these two are in series with each other. All right, so up here, I can say that RT, and I can, it doesn't really matter what you call it, as long as you write it down so your assessor can see what you're doing. Series part of parallel. All right, equals, I'll come down, I'll move it across so I can fit it in. RT for the series part of the parallel is R3 plus R4, which will give us 150 plus 450. Excuse me, plus, what was it, 450, and that will give us 600 ohms. Move it across to there. Okay, all right. So the problem is when you've got circuits like this, guys, you're going to need some space in your book. All right, we're going to need space to be able to simplify it. But what we then have is we have the new circuit, which is kind of hard for me to draw, will be coming across like that into our first resistor and out, down like that, across like that, and across like that. I'm not going to draw it over. Well, I'll just draw it there for now so you guys can see what I've done. And then I can then put my rectangles in. Okay, they're not going to be all the same size. I'm just trying my best here. All right. So by doing this maths above, I have so far simplified the circuit that we started with to a circuit which has just a parallel circuit now in the way of the other two resistors there that are in series. Okay. And we need to label it as well. Okay, so we've already down here, we've got R1. We know what R1 is by looking at the first drawing, so I'll leave it as it is just to make my life easier. We've got R5, which again is 60. we've worked out our new resistor, okay? So it doesn't really matter what you call it. You can call it R series, you can call it, our next one will be R6 if you wanted to call it that. It doesn't really matter. I'm going to call it R6. I'll write it down up here as well, that R6. So it makes sense up there. It doesn't matter what you call it though, okay? As long as you know what maths you've done to get it there. All right. R2. Okay, so now we have the circuit there without the values in. All right. So what's our next step? All right, so the next step now for me is I need to look at this circuit to see if I can work out the current. I look at it and I can't, all right? There's still a series and parallel parts to it. So now I need to be able to simplify some part of this second circuit to see if I can get the current doing it that way. All right, now once again, I start at the beginning, I look at R1. R1 is in series, right? Series, if you can remember, guys, are easy to work out. If you look at the top, we're just adding, all right? So we don't really want to change the series unless it helps us like it did previously. All right, so R1 there can be left alone. Now these two in the middle, R2 and R6, they're a bit of a pain, right? Because they're in our way. If we can turn this into a single resistor, that's going to leave us with 3 resistors in series, which we can add up. All right, so that's where we want to get to. Okay, so if I come underneath, now I'm doing what's in the second circle now. All right, so my resistance total of the parallel is going to be 1 divided by RT equals 1 divided by, now it's not R1, not R2, like our formula usually is, because we're not using R1, we're using R2 and R6. So just be careful with that, all right? That's an easy way of making a silly mistake and using the wrong numbers. All right, 1 divided by R6. Okay. So if we bring that down, it'll be 1 divided by RT equals, and then put our numbers in. So R2 is 400, and then plus 1 divided by 6, which was 600. Okay. Okay. So from here, you guys should all know how to do this. All right, what I'm going to do is I'm going to do an equals, and then I'm going to do my long line. Above my long line, I'm going to write my 1 plus, oh, excuse me, no, I'm not. This is harder to do typing than it is. Yeah, no. Remember, so I'm going to put my common denominator at the bottom, the largest of the 2 resistors. So 600 obviously larger, and I've got my plus in the center, which I can bring down. Okay. All right, for the next step, I need to do 2 things. I need to do common denominator, which is 600 divided by the first resistor. Then I need to do the common denominator, which is the big number down the bottom, divided by the second resistor, which was 600. You guys know that I'm someone who always uses a calculator. All right, so our first one there would be 1.5, and obviously that second one then would turn to be 1. So 1.5 goes underneath the left-hand side because that's the 400 bit of maths we did. So I can write that in there. Just going to push my plus across, so I'll bring him back. Come over to the other side, and then I'm going to write the number in, which was 600 divided by 600, which is 1. Okay, so that's what we've got on the top at the moment. Get rid of that at the bottom. That brings us down to the next line. I'll make some bit more room, which equals, so we've got 2.5, adding those 2 up, and then we've got that. Over the 600. All right, that's what that adds up to. Now remember, guys, once we get to this part here, we need to invert it, which we need to make that a little bit smaller. From that point there, we need to flip it upside down. Okay, so at the moment we've got 2.5 over 600. We don't want it to say that. Okay, we want it to say equals 600 divided by 2.5. And that is going to equal 600 divided by 2.5 is 240 ohms as your answer there. Okay. Remember, I'm working out the parallel circuit. Okay. Now, you guys should know that the resistance total of a parallel circuit will always be less than the smallest resistor. Now, my smallest resistor of the two, one was 400, one was 600. The smallest one is 400. So my answer must be smaller than 400. I've got 240, which it is. All right. Okay, so I'll come up the top to this circuit here, which I've been working on. And what I'm going to do now, which is good because I've got the computer, is I can now get rid of this bit. And now I can draw, and it doesn't matter about the size, guys, all right? It's just easy. I'll just draw a resistor. I just draw a resistor to fill the gap. It doesn't matter that the resistor is bigger. It's just me being lazy, not changing it. Okay, so I'll put my text back in because it's disappeared on me. So I've got an R1. That is the one that hasn't changed from the picture, the first where we started. We've got an R5, which is 60, okay? Now we've got this new value, all right? And this new value is the outcome of the simplified circuit we just did. So we simplified the parallel part, and it turned out to be 240. All right, now we've used all the resistor numbers so far, so I'm just going to use resistor 7, okay? Doesn't matter one bit. You can use whatever one you want to use, okay? So now I've simplified the circuit again. Now I've got 1, 2, 3 resistors in series, okay? Now we remember from our previous class that resistors in series can be simply added up. All right. So once again, let's get our equation right though. So now we've got RT. Okay. You can write series in if you want to. You don't have to. But make sure you get the numbers right. So now I've got R1 plus it's not R2. It's R7. Okay. And then it's R5. Okay. So we've got R1, which is 100. We've got R7, which was 240. And we've got R5, which is 60. All right. So 60 plus 240 is 300, plus the 100 we've got there is 400 ohms in total. All right. So this circuit, which I'm now going to erase all the junk off. So this circuit that we started with here, all right, if I connected it to a voltage source, having it like this would be exactly the same, or the same as RT of this simplified circuit at the bottom that we drew at the start, being equal to 400. Obviously I can't do the symbol because I'm typing, right? But you get the idea. This circuit down here, I'll draw the arrows in. These two circuits would behave identically. All right, so we've simplified this complicated circuit to look like that. Okay, that's just the resistor part though, obviously. But now I can work out the current, okay? Which I'm not going to do at this part here. We're going to do that later on. But that's what we've done first, all right? Resistance is the hardest part. Once we get rid of the resistance, we can then work out the rest, okay? But we've done that there. All right, so we had an answer of 400. I think the answer is on the following page as well. So let's see and hope that I got it right. All right, let's move on. All right, okay, so like it shows here, it shows the 3 stages. All right, 3 steps to reduce the circuit to one with only series resistors, which is what we did, okay? We had our initial circuit at the start. We changed the R3 and R4. We added them together like it shows there. That gave us 600. That made a parallel circuit. We made the, it's called R equivalent there. You can call it resistance total of parallel. It doesn't matter, all right? There's no issues with what you call it there. And then we did that, and then that left us with, like we had earlier, 100 plus 240 plus 60. All right, so we did that, and we got it right. Well done. Okay, this is another circuit example. Okay, so don't be too worried about what the circuits look like, guys, because there's always a way that we can simplify them. First off, the circuit can be simplified to an equivalent parallel circuit. All right. Let's get my draw function going. So look, what it's saying there is that R1 is in parallel. That's great. This second leg is also in parallel. All right. And if you look, and I'm going to highlight the cable so you guys can see it. If this was red, can you see that the red is connected to R1 like that, and it comes along also connected to R2, but it also comes along and it's connected to these two. It goes through there. Remember, the black is only on the return to the battery. So I'm just going to color in all the bits that are red. All right. Once you see which bits are in red, now you can see our problem. All right. You can see that, oh, well, I can't just work it out, add them up or whatever. All right. So those would be the red cables. Obviously, I'll draw in the black. And as you can see, R1 is nice and easy. There's nothing in its way. That's why we don't need to do anything to it. All right. I'll have a look at these two. So these two are connected in parallel at the bottom. All right. These two would be great if they didn't have R2 in series with them. All right, and then same thing over here. They've just drawn this to try and confuse you a little bit. This, the way that looks there, as you can see, the red is coming in and going out. It's identical to it being vertical. They've just drawn it. I've made a mess there. They've just drawn it horizontal this way. It would be the same if it was going that way down the circuit. All right, it wouldn't make a difference. Okay, so what are we going to do first? All right, well, let's clear all the drawings so far to get back to where we started. Okay, so let's have a look to see if we can simplify. All right, so remember, R1 is fine. We don't need to simplify that. The second leg of R2 is a bit of a pain. I need to find out what I can simplify. Now, R2 is in series with R3 and R4. All right, so that's a pain. So what I need to do, I need to make sure that I turn those two into a single resistor. They will leave two then in series. I can add them up, job done. I also need to turn these two into a single resistor. All right, I need to do that. Okay, so let's have a look at that. So first off, we're going to look at these two. All right, so it's a parallel circuit, guys. I'm not going to write the same thing in every time, but it's going to be 1 over RT equals 1 divided by, it's R3 that we're looking at there, plus 1 divided by R4. Okay, that hasn't turned out to be an equal sign, which I'll just change. All right, okay, so coming along to the bottom, this equals 1 over 300 plus 1 over 700. Okay, so that comes down. Let's do our line. Underneath the line goes the biggest number of the two, 700. And then on the top line, let's just bring it down a bit. On the top line, once again, I need to do those two calculations. Okay, so the calculations are number at the bottom, highest number divided by one of the resistors, and then 700 divided by the other resistor. All right, you'll always have the way I teach you guys to do this. You'll always have one of them, which is 1. All right, Once again, you know what I'm like with the calculators. We've got 2.3 there. So we've got 2.3 and 1. All right, so let's write those in at the top. So I got 2.3, bring it back, and 1. All right, I'll get rid of that for us. So that leaves us with 4.3 over 700. All right. Okay, I'll just bring this down to give me some room. And remember, all right, this is where a lot of people make mistakes, okay? It's just silly mistakes. Is now I've got 4.3 over 700, remember, and we need to flip it upside down. Okay, so 4.3 over 700 flips to be 700 divided by 4.3, which gives us a resistor total of that part of the circuit, 700 divided by 4.3, 162.8. All right, so let's double check. We know that that number that we work out has to be less than 300, and it is, all right? So the problem is here that it's hard for me to draw in, all right? Unless I do this business. All right, so just clear this out of the way with a white circle, and then that should, there we are. So that allows me now to show you what I actually just did. All right, so that means that my line will come too thin. Line comes out of R2 and connects with the bottom. I'm drawing it all in black, all right, guys, don't worry about that. And then I've got my new resistor there. Okay, so that now is the result of the maths that I just did, and I haven't labeled it a number yet. So I've got R1, R2, I had R3 and R4, they've gone. If I want to, I can call this R3. You can call it that if you want to. You can call it R8 because R7 is used over here. You can call it RP if you want to, which is the resistance of the parallel. Like, I don't really care. All right, I'm just going to call it R3 for now, and I know that that value there is 162.8 ohms. All right. Okay. Now, what I can do, just to make sure I finish this part before I move on, is if I go down here, I can say, so R of series circuit R2 plus R3. Oops, that's what I want to do now, isn't it? All right, you can see that those two there, which if I draw a circle around them, these two now are a series circuit. So let's simplify that. All right, okay, so we've got RT for this part for us equals, I could even call it R2 because R2 is going to disappear, but I'll call it RT for now. Equals R2 plus our new resistor, which I've called R3, 190 plus 162.8. Once again, I should be able to do that in my head, but 162.8 it gives me 352.8. Okay, so there's my second leg going down there. All right, now I'm just going to delete that. I'm going to delete that. All right, and what I'm going to do is I'm going to attempt to draw a circle which is going to cover all of that stuff. Okay, And what I can do from there now is I can draw in my new resistance, which will go like that and like that. And we're just going to do the box, which is there. All right, you can call it what you like. To keep it nice and easy for us, I'm just going to call it R2. All right, the value for R2 is over there, which is, I'll write it in because I will forget, 352.8. All right, so there we go. We've simplified this part now down to a single resistor. Okay, so this single resistor is the same now as R1 in connection, not in size. All right, so that bit's all good. Okay. Okay. All right, so that leads us on to this next part. All right, and I've circled the bit that I want to start with to simplify. All right, so we're going to say RT of the series part there is R6 plus R7. Let's get that out of the way first. Okay, so that will equal 150 plus 415. Okay, those are the numbers we had last time. All right, so once again, I need to get my circle and I'll get rid of this. That's the wrong color. Okay, so let's draw our new resistor in. So I'll come across to there, come across to there. And we can write down what have we got so far. We got R1, we got R2, and we got R5. So I can call it R3 if I want to. It doesn't really matter. As long as you guys match what you call your resistors to your maths, then that will be fine. Okay. Now then, what do we have? All right, so let's have a look what our circuit looks like now. Okay, we've got the red in and out of R1, in and out of R2, in, out of R5, in and out of R3. All right. And if I do the colors. So actually what we do have now, I know it may not look like it, but if we understand the way things are connected, we do have now a simplified parallel circuit. Can you see that one side of your resistor is connected to red, one side of your resistor is connected to black? All right, and there's nothing else in the way of any of these resistors. Okay. Well, we can again simplify this further, all right, guys, because we want to be able to work out how much current is flowing. Right now, to be able to work out how much current is flowing, we need to simplify it down to our basic circuit that we've been talking about, which again I'll just do quickly on this side, very quickly, so don't expect it to look beautiful. I'm going to use the rectangle, guys, because it's a little bit easier for me. All right, so there's our simplified circuit, okay? So we don't have any other values other than resistors, so we're just going to put this in for now. All right, so let's simplify this last one. All right, now this now is a parallel circuit. So I want to say that 1 over RT equals 1 over R1. R1 looks good, plus 1 over, what did I call the next one, R2, plus 1 over R3. It doesn't really matter which way around you put them. 1 over R3. Let me just move it across because I've run out of room. And we go plus 1 over R4. Okay. Over. Let's write the values in. So 1 over R1 is 120. I always do it like this, guys. I always do it by step, so your assessor can see what you're doing. It also helps then if you do make a silly mistake, that we can see how you made that mistake. R3 is 600. And then 1 divided by, am I going to fit it in? 400. No, I'm not. Let's bring it over. Okay. All right. So we've done this several times already today. Okay. So we put our line at the bottom. We want to pick our largest number to go underneath. I've got 120, I've got 352, I've got 600, and I've got 400. So 600 is going to go there. The pluses are going to come down. So this is going to be a bit of a pain for me to write. But I need 1, I need 2, I need 3 pluses. All right. 3 pluses there because there's 1 there, there's 1, there's 2, there's 3. They come down. All right. Now I need to do the maths for each resistor. So that means that the common denominator, or the biggest resistor, divided by the first one, which is 120. I need to do 600 divided by the second one, which is 352.8 equals. I need to do the third one, which is 600 divided by 600. It's a good one. And the last one, 600 divided by the last resistor, which is 400. All right, let's just quickly do that. So 600 divided by 120. We got 5 for the first one, 5 there. So 5 goes, if it lets me click on it, 5 goes there. All right. The second one is 600 divided by 352.8, which gives me 1.7. So in there, if it fits, 1.7 will go there. Let's just move that across, stuff it in there. All right. Okay, so obviously the next one is 1. 1 goes in there, and that leaves me with the bottom one. This is 1.5. You can see where I'm getting these top line values from. Okay, 1.5. All right, so 1.5 plus 1 plus 1.7 plus 5. So let's delete what we just did here. All right, bring down a new line, and we're going to have equals, and the top line is going to add up to 9.2 divided by 600. Okay, so you know what we do next. Flip it upside down, and that is going to give us equals 600 divided by 9.2, which ends up to be 600 divided by 9.2, gives us a total of 65.22 ohms in total. Okay, let's do just do the check. All right, 65 ohms is our RT total over here. All right, is it smaller than the smallest resistor, 65.22? Yes, it is, because the smallest resistor is 120. All right. All right, so we've got what was quite a complicated looking circuit there. We've been able to simplify it, all right, into something that looks like that. Okay, all right. Now let's just clear all drawings there. Okay. Now, once we've done step 1, once we've completed our step 1, which is simplifying the circuit to find the resistance total, we then need to find the current total, which is IT. All right. Now then, we knew that this circuit, excuse me, simplified to be 65 ohms, but we don't have a voltage, all right? We need the voltage and all that kind of stuff. So what I'm going to do, I'm going to leave what we've done so far to just be able to teach you guys how to work out the resistance, okay? I'm going to pause the recording for a second, and I'm going to restart the recording shortly to work out another example where we move into using current, voltage, and so on. Okay, guys, welcome back. You should be able to see my shared screen, all right, which is the PowerPoint slide with an assessment or a question on it, which is quite similar to the one in your assessment, all right. So what we've got a 12-volt battery. We've got resistor 1. I haven't written the word ohms in, all right, because it messes up my diagram. I haven't got the symbol when I'm typing, all right. So I put out the values at the top and then just the numbers on the actual drawing. Okay, so we've got a 12-volt battery, which is supplying R1, which is 4 ohms, R2, which is 6, R3, which is 12, and R4, which is 8. Okay, and obviously this is, because it's this lesson, is a series parallel circuit. All right. So what I want to do with this is I want to be able to, I want to find, these are what I want to do. Okay, I want to find RT. I want to find IT. All right. Now IT, let's just draw it on the diagram. Okay. IT is there, but whatever that value is, it starts, it goes through there, it goes through there, it gets to this point. Now, because R2 and R3 are different, you're going to have a value of I1, which goes this way. And you're going to have a value of I2 that goes this way. All right. Those two will come together to make up IT again at the bottom. All right. So I'm going to label them as IT, and then I'm going to label it as I1, and label it as I2. Okay. So up here, I'm going to write down that I want to find I1, I1, and I2. Those are the three things I want to find for current. Okay. All right. What else is there to find in the circuit? Okay. Well, I need to know my voltages. Okay. Now you guys know that in a series circuit, the voltage will split up depending on the size of the resistors, and it all adds up to the battery. In a parallel circuit, you just get the battery voltage across everything. Well, this is different, all right? You're going to get a different value of voltage across these, all right? We're going to talk about that now. What voltages are we going to get? Or do we need to find? We need to find V1. Oops, V1. We need to find V parallel, if you want to call it that. And we need to find, I'll call it V full, just because it's in this area. So V1 would be here. Voltage dropped across there. Remember that the battery provides pressure and the loads use that pressure. We just got to find out how much pressure the load uses, okay? We're going to have, because it's R4, I've called it a voltage 4 down there too. And in this area here, now this is a parallel circuit, which means whatever voltage is here is going to be across R2 and R3, because they both share the same cable. All right, the same cable goes in, same cable that goes out. So if there's 10 volts here, then there's 10 volts across R2, 10 across R3. If there's 500 volts there, which there can't be because of the load, but regardless, whatever voltage we work out to be here is going to be the same across the two. And I'll show you how to do that shortly. But I'm just going to write in the center there that VP is where the voltage is going to be. All right, and if you make it easier. All right, it's a bit big. VP is, if I was to put a tester from there to there, there to there, it would be the same amount. All right. V4 would be across those two. Don't know if it's going to make it look harder, all right, but that's how we would measure V4. This is how we would measure V1. VP, I've drawn the arrows. Let's get the red out. That's how I would measure that, and that's how I'd measure that. All right, so if I was to use a voltmeter at these points, then these are the three voltages I need to find. All right, which brings us down to the last thing we need to find is the total amount of power consumed by the circuit, which is PT. All right, now how many loads do we have? We have 4, R1, R2, R3, and R4. So we're going to have 4 values. We're going to have a P1, we're going to have a P2, we're going to have a P3, we're going to have a P4. All right. Once again, all right, I may have done this previously, guys, drawn a bubble around where we're working. I'm going to write down where these things are. So P1 is up there, P2 is here, P3. Notice that the numbers match the resistor that they're next to, all right, which is always an easy way of doing it. All right, so for this example, these are the things that I need to work out. Okay. All right, so I'm going to do this for you here, and this should really help you with your assessment exercise. Okay. Step 1, we need to find RT. All right. I'm just going to draw in down the bottom what I want to turn this into. All right. So I think if I draw it here, it's not going to get in my way. So remember, this is whether you want to call it equivalent circuit or whether you want to call it total circuit, or I don't really care what you call it, because what we want to do, this is our simplified circuit. All the values of T will be on this circuit for us to use. All right. Excuse me. Okay, so just draw my RT resistor in there. Doesn't matter that it isn't shaded in. I picked the wrong one. All right, and we can put some information on this already. All right, do I have any T's at the moment? Well, yeah, I have a 12 volts. All right, so I could say that VT. There we go. I've got one. Okay, there's a good start. What else am I going to have in here? I'm going to have IT. Just do it there to get it away from the other ones in there. Oops. So we're going to have something there. We're going to have something here. And I'll do the P, the power, in the middle as well to keep it out of the way of everything else. All right. As you can see, there's 4 things there. At the top, do I have 4 T's to work out? I've got an RT, there's 1. I've got IT, there's 2. I haven't put find VT because it's given, and then PT. So there's 4 things for us to work out. All right, 4 altogether. I've got 3, and we've only got 3 down here because T for volts is already there. All right, but in order, we need to find RT first. Okay, so this comes back to my previous slides about simplifying. All right, now if I look at this circuit, now I want to get rid of all the junk on it. All right, to try and make it a bit easier for us to read. I don't know how this is going to go. Let's get rid of all that. Undo. All right. Because what I just showed you guys about apologies. I just want to get rid of all this stuff so we haven't got too much that we're looking at. All right. Leave it like that for now. All right. So RT. I'm going to find RT. All right. So which bit is going to be the bit that we can simplify? So starting at the battery, always start there and come around. So we have R1, which is a simple resistor in series. We come down, we've got a parallel circuit here, come through, and then we've got another resistor. All right. So to me, what I would like to do if I circle in red so you guys can see it, if I was to simplify this section into a single resistor, then I would have 3 resistors in series, all right, which means easy, add them up. Okay, so find RT. So to do that, I want to find RT of parallel circuit. Okay, to do that, 1 over RT, you guys should be pretty good at this now, equals, let's have a look, 1 over R2. Remember, it's R2, not R1, because of the circuit that we're working on. Okay, 1 divided by R3. Okay, that brings us to, let's put the numbers in. So 1 divided by, what was R2? 6 plus 1 divided by, what was it on 12? Okay, so here's my long line. Biggest number of the two, 12 and 6. 12 goes underneath. Okay, just going to bring that down a touch to give me some space. I can bring the plus down, and I can say underneath, for anyone who's not sure, remember the biggest numbers there divides the first resistor, so 12 divided by 6 would be 2. And then 12 divided by 12, bit of room, that would give us 1. All right, so those 2 values there are what I write at the top. So 2 goes there, and 1 goes there. Okay with that? Okay. All right, so that equals on the next line. 2 plus 1 is 3 divided by 12. All right, make sure we don't make the mistake of getting ahead of ourselves and entering that in. All right, we want to make sure that we always flip, which means I've got come across from there. So I've got 12 divided by 3, which gives me 4 ohms. Okay, this double check. Is 4 ohms less than the smallest? The smallest there is 6, so that is looks pretty good. All right. So what I'm going to do, I'm going to draw on our main circuit that resistor that we just worked out. I'm going to draw it in red. All right, and the reason is because we need it to stand out, because we need that value for something I'll explain in a second. So my new resistor there, which is the red one. It doesn't really matter what we call it. All right, I'm going to attempt to draw on it. So R. We've got 1, 2, 3, and 4 so far. So yeah, I can call that R5. And next to it, I can write 4, just so I don't forget. Okay. All right. That isn't the RT of our circuit down the bottom. That's just the resistor total of that circuit. All right. So we can simplify now. All right. So what I want you guys to do is to try and look at this circuit. I'll get rid of all that stuff that I just done. All right. I want you to look at this circuit now, starting at your battery. Let's get rid of the circle. All right. Starting at the battery, following around through resistor 1. Then we get to resistor 5. We've got rid of this one and this one. We have this circuit now. All right, that's what we've turned it into. All right, now with this circuit, we can simplify it, and that will give us our RT. RT of series. I'll do RT again, and then we'll break it down into of series. It gives us RT equals, now let's look at the numbers. All right, it's R1, it's not plus R2, it's plus R5 is the new resistor that we've called it, plus R4. That gives me a resistance of 4 plus 4 again, plus 8, which gives me 16 ohms. Okay, that is our number down the bottom. There's our RT for the total. Okay. All right. So I'm going to leave the circuit like this for a minute. I don't want this to confuse you guys too much. All right. I'm just going to leave this here for a minute because we need R5 to work out the voltage in the parallel. So remember we had, now we've worked out 16. I'm just going to go back. All right. So I want my circuit back to how it should look, which is there. Okay. Oh, where's the values of those? There it is. Okay. Get rid of that. Get rid of the circle. That's so annoying. There. Sweet. Okay. All right. So I just showed you guys how to work the circuit out by looking at R5, and I'll write that back in. So that worked out to be 16 ohms. Okay, there's my total. We've got that. At the top, we can, if you want to, do a little tick to say we've done that. Okay. All right. And now I have a 16. All right. Now I can work out IT. All right. Now remember, guys, all right, if you don't know where I'm getting this information from, you always need to have these two things written down. The top one, most important. The second one, important, but there's several ways you can do this the same one. I'm just going to draw them in, all right? So we got V at the top, and we got I at the bottom, times by R at the bottom, all right? The other one we'll use for power, which is P at the top, and then V times I at the bottom. Okay. Now, guys, if you're not sure, which you should be at this point in the course, if I want to find any one of these values in the triangle, so if I want to find I, for example, then I cover I so I can't see it, and that leaves me with V over R, or V divided by R. Okay. If I want to find R, I cover it. V divided by I. V over I. And finally, if I want to find V, I cover it. I times R. All right. So that's what we want to do. All right. Just a quick recap there. All right. So I want to find IT. So my IT, my current total, remember, which is measured in amps, was going to be my VT, because it's a T, it's a total value. Right? So it's V divided by RT. Do we have those values? Yes, we do. We have a VT, which is 12 volts from the bottom picture. And we have a 16, okay? 12 divided by 16, excuse me, gives me 0.75 capital A for amps, okay? All right, so I'm gonna write that in over here. 0.75 capital A for amps. All right. So up the top, I can, to say that I can cross that out if I want to. I can say that I've done that one. I've done that one. All right. So I need to find I1. I need to find I2, and this is the order I'm telling you to do this in, guys. All right. But you don't have to follow it like this. Okay. And what I mean by that is, if I look at this bottom circuit now, I still need to find PT, which is over here, all right? So it's later on in my steps at the top. But if I'm looking at it, I can say, well, all right, what do I need to find VT? I need my triangle, so I need to cover P to see what I need to use. All right, well, cover P leaves me with V times I. Do I have a V times I at the bottom? Yeah, I do. So I can say PT equals VT multiplied by IT. Okay, those values are 12 times 0.75, which gives me 9. And remember, it's W for watts, capital W. I'll write that in there. All right. So just a bit of a recap, all right, guys. Your currents, I1 and I2, I'll write a few rules in that we must have. All right. Let's have a few rules, okay? So I'm going to write them up here. So IT equals I1 plus I2. So whatever current you work out for I1 and I2, they have to add up to 0.75. PT is going to be, sorry, let's do the V's first. VT must be the, and this is the bit that catches people out. It isn't V1, V2, V3, and V4 because R2 and R3, which is the parallel circuit, they share the one voltage. All right, so we called that VP earlier, the voltage. I'll do a circle so you guys can. So the voltage in this area, okay, is the same across both resistors because they're in parallel. Like 230 volts comes out of every power point in your house, it's wired in parallel. So they all have the same voltage. All right, so VT is going to be the voltage drop at R1, which is V1, plus VP, plus V4. That will add up to there. We can write down next to it, PT equals, and there's 4 loads, so we're going to have P4. I hope that hasn't gone over anything. No, that's okay. All right, so these things are going to be your way of finding out if you get this stuff right without the need for an assessor. All right, that's the idea. Okay, so let's have a look at my actual circuit, the one I've been working on. All right, now what I can say is that IT, which is 0.75, is at this point here. All right, now I'm going to draw over the top of this circuit in a different color. Let's do it in yellow, right, which we haven't used yet. All right, so 0.75. Remember, guys, the rule is that a series circuit, let's write it up here, series current is the same. If everywhere is not a term that I would like to use, I would say in all parts of the circuit, but I wouldn't have fitted that in. All right, so let's go back to my my color. All right, so the current that starts at this point here, let's get a color that's darker than that. Let's see if I can use that one. Sweet. All right, so this current here when the circuit is on is 0.75. That same amount of current goes from there. It goes through R1, which is 0.75, and it comes along to this point here. All right. Whereas in the real circuit, it splits down I1, down I2, and then it comes back again at 0.75 through there. Okay. Now then, this is a really, really important point. You will remember, and I've left it in for this reason, that when we simplified the parallel circuit, we had an R5, which was a combination of the two. R5 was 4 ohms, all right? Well, if I didn't have this parallel circuit, the current would have kept going, okay? And this current, which I've just drawn in here, I'll do a circle around it. This bit here, guys, is what we need to work out VP. All right. So what I'm going to do first, I'm going to work out voltage drop 1 first, which is going to be up here. Remember V1 next to R1. So I'll do the maths over there and then the numbers at the top. So V1 equals, okay, so what's the equation first? All right, so it's I times R. But before we go any further, which I do I want to use and which R do I want to use? Well, if I look at the pink in the circuit, that's IT that's going through there. It's got nowhere else to go, so IT has to go through. So I'll put a T next to that. Which resistor are we looking at? Well, we're looking at, where's that gone? We're looking at this resistor here. So we're looking at R1. Right. That hasn't worked. Okay, so V1 equals IT times R1. All right, so underneath, let's put some values in. So we've got 0.75 multiplied by R1, which is 4. And that gives me 3 volts there. Okay, so I can write, if I get rid of the circle, I can write down I'm going to write V in because I can do that. I don't have ohms, remember. All right, so I've done my V1. Okay, the next thing I want to do is not V2 and it's not V3, but it is the V parallel. All right, if I work out the V parallel, then I know what the voltage is across both of those. All right, this is the bit that can confuse people. All right, so VP, remember we need I times R again. All right, well, which I and which R? All right, so look at the pink. It's going through R5. R5 was the equivalent that we calculated earlier. So that's the resistor we need to use to work out how much voltage is dropped at this point across here. All right. Sorry, I just accidentally clicked that, so I'll need to delete it and start again. VP. All right, coming back to this point. Okay, so VP equals I times R. All right, so I is going to be IT again. This time R is R5. All right. Okay, so let's work out what we need to do for these values. All right, so IT, once again, is 0.75. Multiplied by, what was R5? R5 was 4, all right? So same value as previous, which equals 3 volts. 3 volts there. Okie dokie. All right, so what have I done now? So at the top, I've worked out V1, I've worked out VP, and I haven't worked out V4. So let's do V4. We should all know what we're doing now, but we'll go forward anyway. So I need I times R again for V4, which is down the bottom over here. So we know the voltage there. We know the voltage there. I haven't written the VP in, but we've got our answer here, which we'll use shortly. Now we want to do V4, which is the bottom. Which I do I need? Well, if you look, it's the total amount because this is part of the series circuit. IT. Which resistor? Well, I'm looking at this one, so we need R4. Okay. 0. 0.75, which is IT, multiplied by R4, which is 8 ohms, gives me 6 volts. Okay. All right. So I've got across the parallel leg, I can write in VP. 3. Okay. And at the bottom, I can now write in that V4 equals 6 volts. I hope you guys are keeping up with me here. All right. Okay, so we can now do something else. All right. First off, I can cross off V4 and PT. We did that earlier. All right. But now we have the VT one up here that we can try to see if we've got it right, okay? So at this point here, I can say that VT should equal to V1 plus VP plus V4. 12 equals, what do we have? 3 plus 3 is 6 plus 6 at V4 is 12. All right, so our voltage drops there have all worked out, and we're happy with that. Okay, all right, let's erase or try and erase what we've done here. Okay, now let me see if I can get rid of this bit. It's not going to be easy. Get rid of that. Get rid of this. We don't need this R5 anymore. R5 we needed to work out the voltage, sorry, VP. Now I've used it, I don't need it anymore, so I'll get rid of it if I can neatly get rid of. Beautiful, excellent. Okay, all right, so looking at my circuit now, what have I got left? All right, so P's are always last, all right, because we need the V and the I. Now I need to work out I1, okay? So I1 equals, what do we need? We need V over R, all right? So let's write V over R in first. Okay, but which V and which R? Well, I1 is the current which is traveling, and I'm going to draw it in orange. I'm going to try and draw it in orange. I1 is the current that goes through there, through this resistor, and comes back to here. All right. Whereas I2 is the current that leaves this point here, goes this way, in green, and then comes back to there. All right. So we need to work out these two colors. So I'm going to do the text for. I need to delete that now. I'm going to do the text in the same colors as the current is drawn. So I1, which is that arrow, that's what we're working out, is V divided by R. Which V? Well, it's VP because it's part of the parallel circuit. Which R? It's R2. Okay. That equals VP is 3 divided by 6. That gives us 0.5 amps of current that flow that way. Okay. Okay, so 3.4, I can write that in at this point over here. So I1 equals 0.5 amps. That's gone too far. Let me just move it over so you can see it. There we go. It's going down that way. All right. Now, a quick recap. All right. So the smaller resistor is going to let more current through. All right. 6 is half the size of 12. So we know that twice as much current is go down this way than that way. All right. Now we can work out the current going through R3 by just taking away 0.5 from our total current, which leaves us with 0.25. Right, but we'll do it the correct way anyway. So we're going to have now in green I2. We're going to have let's remember that it's V divided by R. I always remember that from the triangle. Okay, but which V? It's VP. VP, because it's the parallel, remember they both got the same voltage. This time the R3 is 12. Sorry, VP over R3. That takes us down to the next line. So our V, once again, is 3 divided by 12, gives us 0.25 amps, which I can write in there. I equals, sorry, that's I2, I equals 0.25 amps. Okay, so now I have another part of this at the top, these rules. And I want to make sure that IT equals I1 plus I2. If it doesn't, remember, I've made a mistake there. If it doesn't, remember we've lost current somewhere, and what is going to pick that up in the circuit? The RCD will notice that. All right, and that's going to tell us. Right, so our IT was 0.75 equals 0.5, 0.25, which does work out. Okay, so our rules there for I have been satisfied, and so have our V's. Okay, so we're doing well. Okay, so now we just need to work out the final the P's. Okay, so let's get rid of that, and that. Once again, guys, this is recorded, right? So if I'm going too fast, obviously pause it so you can write down your notes. Okay, but this example I'm going through here will definitely help you with your assessment question. All right, okay. On my draw function, I'll put it back to black, and I'll get rid of I1 because we did it, and we did I2. All right, which leaves us with the bottom ones. Now we can work out the last four, add them up, and they've got to equal PT. Okay, so remember we're using the bottom triangle this time. So I'll use my black right here. So P1 we need to work out. So P1 is V multiplied by I. Okay, so this is where people go wrong. It's the which V and which I we looking at. All right, so P1 power is in this area here. So those are the values we need. P4 is going to be there. P3 is going to be in this area, and P2 is going to be with this information here. All right. Okay, so I didn't have to delete that again because I waffled on. Let's go back. All right, let's go there. All right, P1 equals, let's have V times I from the triangle. Okay, now we're going to pick a V. It's V1 at the top. Multiply by I. The I is the pink flowing through, which is the total amount, which is IT. All right, so V1 is 3 multiplied by 0.75. All right, let's not laugh because I do everything on the calculator, just in case I make a silly mistake. 3 times that is 2.25. Let's get our units right. It's watts. P2 equals V times I. All right, let's have a look at which ones we need to use. So P2 is in this area. All right, so be careful because we are not using IT and we're not using V1. All right, what are we using? Well, we're using VP because it's a parallel part, and we're using I1. All right, because that's the current going through R2. All right, so that's going to give us the that's 3 times a half, which gives us 1.5 watts of power going through there. Let's have a look at P3. So P3, once again, V times I from a triangle. Let's have a look which V and which I we're going to use. So once again, it's the parallel leg, so it's going to be VP multiplied by I2 this time, which is 3 volts multiplied by 0.25. 0.25 times 3 is 0.75. And that leaves us with the last one, which is V times I, always from the triangle, right? We can work out what we need afterwards. So if I look at R4, I need to look at the V, which is 6 volts, which is what we worked out earlier. 6 multiplied by I. Now notice that I is pink again, which is IT, which is 0.75. Is equals 4.5 watts. Okay, remember now we can fill the last rule in to see if we're right. So P1 plus P2 plus P3 plus P4 should all come back to whatever PT was, which was 16. 16 equals P1, which was 2.25. Let's find the calculator. 2.25 plus, what was the next one? 1.5 plus 0.75 plus 4.5 seem to have made a mistake there somewhere. Bear with me. No, I haven't. Sorry. I've made a mistake reading the drawing. All right. So I read the RT, which was 16. My bad. PT, which is down the bottom over here, look, is 9 watts. That makes me feel a bit better. So 9 watts is PT, 2.25 plus 1.5 plus 0.75 plus that gives me back my 9 watts. All right. And once I get to that point there, I can then cross out all the different things in the example, and that example is finished. Okay. Once you do that, guys, you will then be able to, should be able to complete your assessment question. All right. If there's any issues with that, obviously get in touch with us so we can help you out with it. All right. That's the maths done. All right. So that's pretty much the session done. We're just going to finish off by moving to the next slide. Let's go back actually there to that one. All right. So just a bit of a visual here. All right. What would happen if we had an open circuit in the following locations, right? So there's an example of a series parallel circuit, and you're going to have point 1, which is there. Okay. Now, if you get an open circuit there, current cannot flow through it, which means the entire circuit is going to be switched off. All right. Now, assuming this fault disappears, what's going to happen at point 2? All right. Well, current can flow through there to this junction. It cannot flow down, but it can flow through. So R2, R3, and R4 are going to continue to work. R1 is not going to work. All right. Assuming these two faults clear, point 3, now current can flow through here to this junction, but it can't flow further because there's an open circuit. So only R1 will be working that time. Pretty easy, I think, guys. All right. Assuming that once again that these faults clear, point 4 is there. All right. So current will travel through there to this junction, through R1 and back. So R1 will be working. It will continue from this junction through there, through R2 to this junction, where it can't go that way because of the fault there, because it's open. So R3 will be off. However, R4 will continue to work. All right. You are going to get different values of current at this point because certain loads are or aren't working. But that's the basics of what we were looking at there. All right. Okay, so practical uses, which there's another example in your assessment. It asks for where you would use these types of circuits. All right, so series parallel circuits, an example is batteries. All right, so we've discussed previously that if you connect batteries in series, you add up the voltage, but not the amp hours. So amp hours is how long a battery lasts. So if I was to connect 2 9-volt batteries in series, if they're 1 amp hour each, then it would be 18 volts with 1 amp hour. If I was to connect them in parallel, remember that the voltage then stays the same, but the length of time doubles. So then 2 of these in parallel, would be 9 volts, but with 2 amp hours, so it can last twice as long. All right. This is where series parallel comes in. If you want to increase the voltage together with increasing the length of time you can use the battery, then you would connect it in a series parallel combination to increase the voltage to what you need. So whether that be 50 or 100 volts or whatever. And obviously then you connect as many batteries in parallel to increase the number of amp hours. All right. So for example, if you've got a Milwaukee battery and it says 18 volts, 6 amp hours, then you know that to create that, you've got to have a series parallel combination of certain batteries, for example. All right. This is just the connections of them. We don't really need to go through that. All right. I'm going to stop sharing my screen there, guys. All right. So that's the end of the session today. If there's anything you guys need, obviously send or get in touch with the college, and they will then put you through to me. All right. Otherwise, best of luck with the assessment questions that helps you with. Speak soon.